all the optimizers for this wonderful insurance from all these directions. And as you can see today, I want to talk about the almost metal phase in this system. Actually, I'm now gradually moving towards some other topics, but this is a topic I'm given by Aviat to talk about. So, but we still have some new data, recent data about this. So maybe I can discuss. So after yesterday's debate, I think the anomalous metal phase is still quite like not everyone is convinced. So I just try to show like our progress in understanding and why we think maybe this is still interesting. So this is my outline. So I want to first introduce the technique we are using to introduce superconductivity in the system, and then some experimental results regarding the system. And then in the end, if I still have some time, I want to also talk about what we are recently exciting about this lithium intercalated iron selenide stuff. So let me start by showing a summary of many of these interesting properties, including like quantum effect, superconductivity, and all these features, all these phenomena you can access by tuning the carrier density. So of course, the other way around, you see that some phenomena happens at around relatively low density per square centimeter, and some phenomena happen at high density. So tuning the parameter, one of the parameters important seems to be the carrier density. Of course, you can do other things like the strain or the pressure, but this one is what we want to do by tuning the carrier density. So how to tune the carrier density? So especially in 2D, then we can use a gate, electric field effect to tune the carrier density, or in some other materials, we just put some dopants. But then you need to synthesize different compounds with different dopants or different amount of dopants, which is we call this discrete kind of doping or tuning way. And for continuous tuning, which could be more convenient for studying the physics of the system, then there are, for example, the electric field effect, but this is limited by electric breakdown. So then the maximum range could be like 10 to the 14 centimeter. And then for some other recent technique, which is this ionic liquid or ionic solid, then there are two different ranges. So one is you just use the electrostatic gating, then you can end up having some carrier density around or a little bit above 10 to the 14. But if you can somehow manage to intercalate these ions into the system, then you are not limited by the electrostatic process, so then you can have a higher tunability. So this is what we are aiming at. So what we are doing for solid ionic solid is that we take a substrate or some which has a lot of ions inside, and these ions can be pushed by the electric field if we apply a backing voltage. And if you put your material, especially nowadays these exfoliable materials on the surface, then you have a chance that these ions can go into the material. So this is a pretty simple intercalation process. So what kind of material you can choose is, for example, this lithium-containing substrate, which is developed because recently we are interested in all these lithium battery research. So this is actually developed for lithium battery research, but one can use this to intercalate lithium ions into some materials. For example, this was initially used to tune iron selenide, and then you can reach a high superconducting temperature. And the other tools in our box includes, for example, some solids that contains basically protons, hydrogen ions, and you can use that to intercalate and tune the property. Of course, now we also have like oxygen ion containing substrate, and also recently we also use fluoride, and we can inject fluoride ions into the material. So these are the tools we use. So I'm going to just focus on this lithium substrate, which is kind of nice because the substrate surface is pretty smooth, so then we can put our material on top and then tune the property. So titanium diselenide, this material is constantly giving us some interesting information. So in the beginning, people are interested in this material because it has this kind of band structure that you have the electron band and the hole band, and in the high temperature range, it has the coexistence of this. So this is acting like a semi-metal. But when you cool down below roughly 200 K, then the electron hole, it is proposed or argued that the electron in the electron band and holes in the valence band, they can pair to form excitons. So due to the formation of these excitons, you open up a gap, and then the Fermi level moves to the electron band, to the conduction band. Then you have just a pretty simple electron pocket system that you can study. So many of the research is actually focusing on this external condensate, but what I'm interested in is the superconductivity of this material. So these are by intercalating, or you put some dopants in it by putting copper inside. You can have this nice phase diagram where the charge density wave gets gradually suppressed and the superconductivity occurs. Or you can apply pressure, same thing, that the charge density wave goes down and then the superconductivity occurs. And recently also people use the ionic liquid gate, and from that they see similar phase diagram. And they even see that there are some kind of superconducting networks formed in the system. So our motivation or our starting point was actually not very big. So we just want to ask if we can use the lithium intercalation to have like some phase diagram, how this phase diagram looks like. Because people before use the lithium, but not in a continuous way. Just use lithium, grow the synthesized material with a single lithium content. So here is our device. We exfoliate the flake, horizontal lateral size about the tens of micrometer, a thickness of 50 nanometer, and we put it on this substrate with the electrodes on the bottom. So this is just a single stamp transfers, and then afterwards we just load the sample into our system and so how the gating works is we apply the gate around the room temperature when the lithium is still active, and then after some time we cool it down to below 200 K, usually like 250. Then the lithium ions are frozen, so then we finish the intercalation, and then we can get this measurement of the resistance. And then this is a without the intercalation, we see the typical transition from the semi-metal to electron conductor with a single electron pocket. And then this peak becomes weaker when we intercalate more lithium ions. This is actually a bit strange to us because previously all these phase diagrams show that the charge density wave should go down, the temperature should go down, but we actually do not see that. And at that time we thought, okay, maybe this is just an inhomogeneity because we have the lithium going in some area as suppressed the charge density wave, or some other small areas are still not fully suppressed. However, recently with improved, you still see this effect. So somehow I think this is intrinsic to lithium intercalation, so that the charge density wave, the temperature of the charge density wave does not go down, although the strength of this peak goes down. And then the superconductivity occurs, which is just at low temperature. So if we zoom in this area, if we zoom in the low temperature side, we see that after gating, the superconductivity occurs and becomes better when we go to the optimum dome. So it shows the superconducting dome as a function of the injected lithiums, or as a function of the total carrier density in our system. Some basic facts, like this is still in the dirty limit, so we estimate the mean free path is still smaller than the coherence length, and the maximum PTC is roughly about 1.5 K. And this is 50 nanometer thick. However, if we measure this by rotating the magnetic field to see the anisotropy of the hypercritical field, we still see that it follows the 2D performance. So that is to say that although this is thickness is larger than the coherence length, but you still have the 2D behavior. You can treat it as a 2D superconductor. So one do see that when we apply some field, then at low temperature, then there is this resistance tail this is what we take in the beginning as the indication of the anomalous metal phase. And if you plot it in the standard way of people showing the anomalous metal, then we see that the resistance do show a saturation value when we approach low temperature. So to be honest, at that time, we didn't use like very fancy filters. We just use the room temperature low pass filters. And we do see that if we do not use the filters, then we see a very strong effect. After the filters, we see that there is still this saturation. However, I need to add also that afterwards, we also try this with helium-3 insert together with copper powder filters, which I made. And we still see the same effect. And later on, I will show also data that we measure in the dilution fridge with, I will say, quite good filters. And we still see this effect. So somehow I think this is kind of robust against these filters. And we here also see that the saturated plateaus, they disappear when we go to the overdosed regime. So I would say this is also an indication. It's not the temperature cooling issue, because if we, for the same sample, we can indeed cool it down. We can keep, this is showing that it still goes down and the cooling is still sufficient. And another, yesterday we also discussed, debated that, so if we take this value, for example, this value, which is 4% of normal state resistance, and if we assume this is corresponding to the whole normal state region in between our electrons, then it corresponds to roughly this much, so 200 nanometer of non-superconducting region. And though based on our estimation of the mean field path or the diffusion constant and all these things, then we would expect that this much area should be approximatized by superconducting regions, and it should go down to superconducting transition. It should show another transition around 0.3, which we do not see. So this is also kind of pointing toward the intrinsic anomalous metal. So this is so far the what we see for the anomalous metal. The other interesting feature we see is these oscillations. So previously we showed the data when we fix the field and change the temperature. Now I do the other way around. I fix the temperature and sweep the field. So while the sample goes from the superconducting state to the normal state, it shows some peaks. And these features are quite reproducible. And if I plot them in the color coded plot, then you see that they show somehow like some stripes or some pajama-like patterns. And for another sample, we also try to rotate the magnetic field, or actually rotate sample against the magnetic field. And we see that these features, show at the same perpendicular magnetic field. So the in-plane magnetic field is different, but it does not affect our sample. So this is also indicating some kind of two-dimensional structure within our sample. So some people are more familiar with like LixTiSe2 effect. So this is a kind of like LixTiSe2 effect, but we do not have holes. We do not drill any holes in our system. So it's naturally forming our system. And indeed, it was observed by the ionic liquid gating some time ago that they observe also these oscillations. So this is somehow indicating that this material has this property of showing these oscillations once you go to the superconducting state. And the interpretation or the speculation, so far we don't have spatial evidence. This is purely speculation that the system has charge density wave. Remember that we have the charge density wave extending to the density regime where we have the superconductivity. So the charge density wave have two different types of charge density wave in the system. One is this commercial rate charge density wave, and one is the incommercial rate. And superconductivity can happen only in the incommercial rate. So that the CCDW, the commercial rate charge density wave, they form big domains. This is just not one single commercial rate charge density wave puddle. This is actually a big puddle. And around these CCDW domains, then we have the superconducting networks. And that sort of explain why we have this structure appearing in our system. And
what is the spatial scale of your picture?
Yeah, so this is about 200 or 300 nanometer from the FFT. From FFT, we see the structure has a very big size. This is 300 nanometer. This is actually bigger than people observed in the liquid gated sample. And also the doping dependency is a bit different. I just want to show you this comparison. So what is the connection between the anomalous metal and the resistance oscillations? We think that when we have a 50 nanometer thick sample, then we actually suppress the superconducting fluctuations. And each superconductor has a strong superconducting fluctuations, but when we go to 50 nanometer, we may suppress this. However, once we form these periodic structures, that can enhance because they cut the superconducting region into different puddles. So it can enhance the fluctuations again. Because we do see that the oscillations appear right in the regime where we see the saturated resistance. So they are coexisting in the same temperature and magnetic field phase diagram. So this is our kind of interpretation. And we later on also see this in the underdoped pistol, the high temperature superconductor. We use the same technique. By inject the lithium ions into this, we can push the sample from the optimal doping, TC of 90K, to around this regime, which is like 2 or 3K. And in this underdoped regime, we do see these oscillations. The period is different, but somehow there's I feel there's a link between them. So once you push it to the underdoped with some charge ordering, then you can see the impact. And in fact, recently we also see there's another report from China that they observed this even in niobium diselenide exfoliated flakes. So I feel there is a universal property in this, but maybe this is we still need to check for more materials. But niobium diselenide also this system has charge density wave. So somehow it looks like you have charge density wave competing with superconductivity. You may have this effect. So yes. So then the idea is just reporting our progress along the time axis. So after this, we sort of we start to think how to improve our sample quality because although I showed 2 samples with 5 million, but not all of them show very nice properties. The problem is this intercalation is not very homogeneous process in this particular material. In some material, it looks quite homogeneous that we check different complexes show the same result, but not the case for titanium diselenide. The problem of this intercalation could be that the lithium goes through the holes, defects in the materials. When they push through this holes, they may create some wrinkles or some cracks. Then other things you can see that from AFM study, they also see these wrinkles. This is typical problem for lithium battery that the lithium forms some this secondary compound that is between at the interface between your material and the lithium and the substrate. But it can create a problem. So how to solve this problem? We take the inspiration from these 2 works that people tried also in lithium related studies to intercalate the lithium for the 2-dimensional materials with these interlaminar gaps that the lithium can go between the gaps. So for example, in this study, you can interpolate lithium between the 2 layers of graphene, and the lithium propagation is pretty fast. The diffusion constant can be pretty high. In other study, they do this with zirconium nitride chloride, also the same thing. So they improve the homogeneity of the sample. So how do we do this? In our system, the simple way is we just put our flake on top of this aluminum oxide, which can, from experiment, we prove that it can block the direct intercalation. And then we have just a corner of the sample touching the substrate so that lithium ions go in from this corner, and then it can migrate along our flake due to the density gradient of the lithium. So from the transport, we see that this flake with different pairs of the contacts, we see that the Hall coefficient now from this intercalation process and also the de-intercalation process, they show pretty much the same Hall coefficient. I mean, maybe it looks not to you, but to us, this is already quite an improvement because before we couldn't do this. So that is to show that we have a higher homogeneity. Actually, we also did AFM on this flake, and we can see that the surface looks much smoother. And so with this technique, then we try to combine everything. We try to use the lateral intercalation and also put the contacts to measure transport, the Hall effect, the resistance, the longitudinal resistance. And also we try to put the molybdenum disulfide as a barrier, and then the titanium gold, the small contact, as a tunnel electrode. So then we try to measure both the resistivity and also the tunneling gap. This is actually also to combine this with a dilution fridge. So within our dilution, also, sorry, this is how the sample oxide. So the square area is a living oxide, and then we just put the sample on top. So with this combination, improve the homogeneity and the beta filtering, we still see superconductivity. Also, we still see the saturated resistance. So, I mean, I was always doubting about the almost metal phase, but I keep seeing this by improving our filtering. So somehow I feel that this is something very you can say nasty to remove. So our dilution fridge is really equipped with the thermal pulse cables, meaning that with the magnesium oxide and dielectric going from room temperature down to the mixing chamber, together with copper powder filter and RC filter. So we have all the filters. The electron temperature for this system we calibrated by measuring gallium arsenide, which can go down to 80 milli. So this is plotting everything down to around 100 milli. And then we also can measure the tunneling gap right in this superconducting state. This is not a perfect gap, but we think this is because molybdenum disulfide may not be so perfect as an insulator. However, we do see the gap here in this superconductor. And also once we go to this state where we have like 100 milli-K with 10 millitesla, 20 millitesla, we still see the gap. So this is to indicate that we have within the anomalous metal phase, we still see the gap, and the gap looks quite symmetric. So apparently it shows the electron or particle hole symmetry still in the anomalous metal phase of this. And another thing quite interesting is when we switch the field, this is perpendicular field. We then check that this is purely two-dimensional, that these features, they just respond to the perpendicular field. So I'm showing you that basically the gap, but the color-coded gap, as a function of V field, either going up or going down. You see that these features, they are the same, but they are just reverted. So there is some hysteresis effect in that, probably due to the trapped fluxes. However, these features, they are like rippling around. So when you go increase the B field or decrease the B field. This can be enhanced to appreciate these features by subtracting these two sets of data, and we do see some features, right? So you see here in the middle we have this blue region, and then the pink region, and then the blue and the red, and the pink and the blue and the red. So there is some kind of oscillation. And on top of this oscillation, we also see like finer structures. So there are oscillations and also higher harmonic oscillations. If we do the FFT, we do see that we have the fundamental frequency, and then the second harmonic, third harmonic, fourth harmonic, even the fifth harmonic, they follow the same line. So what is the origin of this? So to us, this is again speculation that for the oscillation, resistance oscillation, we speculate it comes from this little positive effect of the superconducting network. So if you take that picture, then these oscillations, the higher harmonics, means that the Cooper pairs can go around one region, or go around two, or even three, or even four. So that gives you the higher harmonics. So looks like these superconducting networks is quite regular, so that we can have these features. And we think this is also because the tunneling probe is probing a small area, so that we can have this. We can better resolve these features. So my summary around this lithium titanium diselenide adventure is that we can tune. In the beginning, we just want to see if we have the phase diagram And now after reproducing the phase diagram, we see almost metal and together with some oscillations in either the resistance and gap. Okay. So recently, what we are doing is this is going back to lithium intercalated iron selenide, which was initially what people did to demonstrate the technique, the substrate, and we just want to train our students, and by training the student, we check that okay, this is we repeat what people observed before, that by intercalating lithium into this flake, you can enhance the PC from about 90 to around 40K. And then we just want to see if how the carrier density changes. And then from the Hall effect, we see that when in the high TC regime, we see this hysteresis. It looks very much like a ferromagnetic response. If we remove the lithium ions, we do not see this. And if we interpolate lithium ion again, we see this effect. And it shows up also in our magnetoresistance. And we check different pairs of contacts for iron selenide. Somehow it's quite homogeneous, so it does not depend on the contacts we choose. And this is just purely from the vertical direction how we interpolate lithium ions. And then we also collaborate with scanning split team in Shanghai, and they show that the top row basically shows the Meissner effect in the sample. At around 28 Kelvin, we do not see Meissner response in the sample. And the bottom row shows the magnetic, the DC fluxes, how they distribute. Because this is at zero field, we do not polarize the magnetic domains. But it looks like the magnetic domains can coexist with the superconducting region, at least in the vertical direction. Then the resolution now is about 2 micrometer. So somehow I think, and for this system, they can coexist in sort of microscopic way. So this is also why we put our so that this system somehow has both high TC and both high superconducting transition temperature and also the high ferromagnetic transition Curie temperature. Yeah, this is really insane.
Do you have any questions?
So, given that your films are sufficiently thick, have you tried examining whether those lithium ions distribute uniformly across the film thickness?
Yes, that's a very good question and a difficult question. So, the honest answer is we haven't done too much on the vertical axis. So if we want to check this, we can go down to single flake. And yes, I guess that's what I can say now.
So maybe a quick follow-up question: is it technically possible to just do, let's say, STM of both sides of your flake, just turn it around or not? I don't know. And to see whether it looks similar.
Once the flake is on top, it's not very difficult to take it out.
Okay.
Take it out.
So, what I understand from you is correct that I think that in these samples, which there's hardly any disorder, the number can come if you create the situation where you have induced quantum fluctuation.
That's a very good suggestion. So, I mean, there is a clear link between them in titanium diselenide, but we see the oscillations in, for example, Bisco in the underdose regime, but we checked and we do not see anomalous metal phase. Bisco. Here, we would not see the anomalous metal, although we think that there are these organic structures.
The organic structures don't occur. What you said was a fluctuation.
Yes, so the fluctuation comes because of this periodic structure.
Together with maybe.
Yes. Okay. Any questions?
Yeah, question about your little Parkes oscillations. Questions actually. So you mentioned that the fact that you see harmonics would be a signature that your samples are very homogeneous, but I would say if they're really homogeneous, wouldn't then the larger group cancels out, because then there would be currents in opposite directions in the same branch, and then I forgot why did you angular lattice? I think you answered this already.
I didn't mention that. So the last thing, the last question is so, for this material, it's a triangular, has a triangular lattice or hexagonal lattice. Though it has this shape. This is purely speculating. So yeah, for the higher harmonics thing, this is also so far because we see the higher harmonics, so we believe that because of they are going around 2 or 3, 4 triangles.
Wouldn't it be several terms around the same?
So, okay, if they go one side triangle times, they give the same result. Yes.
So do you know people try to do a diffraction measurement to see if they can spot right from this regular path?
So far we haven't done. So it's a good suggestion, but it's not easy to do it.
No, it's not. But if it's true, then you should observe some.
Yeah.
I guess.
I was just wondering, what's the size associated to these? Maybe you already said it, but to these field oscillations.
Okay, so for cuprates, it's roughly around 50 nanometer, and for titanium diselenide, it can be 200 nanometer.
In any way comparable to the size of this sample here or not?
We for at least here, this one we checked the different samples. I didn't have this slide, but they are the same. They show the same period.
Okay.
Even with different doping, it shows the same period. For titanium diselenide, actually they are different. Yes, for different samples, they are different. So.
Thank you again.